Yes. Yes. Oh, excuse me. Okay. Hi, everybody. So I'm Johnny Greco. Thanks for giving me the opportunity to tell you a bit about what I've been working on. So I actually recently graduated from Princeton like 3 weeks ago and have migrated to The Ohio State University, where I'll be starting an NSF fellow followed by a CCAP fellowship. So I'm going to be telling you about our search for very low surface brightness galaxies with the Suprime-Cam survey. So we've heard a lot about UDGs today. I also want to start by just noting that the low surface brightness galaxy population is really a diverse group of objects. They're typically defined to have surface brightnesses that are lower than the night sky, but they span objects from, the biggest spiral galaxies known in the universe, like the very famous Malin 1, down to dwarf galaxies in our local group. And then, of course, including objects like these UDGs that we've heard about today, which I'll also emphasize that we've known objects like UDGs exist for decades, since like the 80s. But we've heard a lot of wonderful talks today, asking the question of how do these objects fit into our current picture. But a very important ingredient into that equation is an understanding of the actual galaxy population that exists. Right? And so this really motivates wide field surveys that have the sensitivity to detect these sorts of galaxies over large areas of the sky. And in particular, you'd love to do it in multiple wavelengths, and including the optical, where you can detect galaxies by their starlight and be sensitive to a wide range of gas fractions to find these sorts of galaxies. So the HSC survey is really well suited for this problem. So we heard a bit about this today from Song. So this is a collaboration between Princeton, Taiwan, and Japan. And it's being carried out with this new Suprime-Cam, which is mounted on the prime focus on the Subaru telescope, which is an 8.2 meter telescope in Hawaii. So this really is an incredible astronomical instrument, but also it's an unprecedented survey instrument for astronomy. And so by the end, it'll survey about 1,400 square degrees, and it's currently really serving as sort of a testing ground for the sorts of data that we're going to get when we in the LSST era. So for my science, I'm interested in what HSC brings to the table in the LSB regime. And just to demonstrate that for you here, I've got some very low surface brightness sources as they appear in SDSS. And so you could sort of see some smudges in these pixels. So here's what HSC sees when it looks in the same region of sky. So it really delivers, and it's providing a new view of the low surface brightness universe. And what's particularly exciting about it is it's providing data like this over large areas of the sky. Now, while these are really beautiful images, they also represent a significant challenge, right? Because the density of sources in these images is really high, and this problem is just going to get even more intense with LSST. And if you're interested, like I am, in finding these very puffy foreground galaxies that are large on the sky, they blend with all these background sources. So currently, pipelines for SDSS and HSC and also LSST, which turns out to be the same pipeline that HSC is using, they shred these galaxies to pieces. So they really aren't doing well at finding these sorts of objects. So for a good part of my thesis, I put together an automated pipeline to go in all the HSC data and find these galaxies. I did this with a combination of new and old tools. So at Princeton, in our basement, a good fraction of the LSST software team is working hard. And so I took advantage of them as a resource and used the LSST code base to do a bunch of initial image processing to clean these images up and prepare them to find the sorts of galaxies that I'm interested in. And then in the end, I found that source extractor was still the fastest path to building a catalog. So that's what I used to do the source detection. And then I do some more detailed galaxy modeling to define a set of parameters and define what we mean by low surface brightness. So our sample selection looks like this. So typically, these galaxies have been defined by their central surface brightness, and we decided to go with mean effective surface brightness instead. And the reason we did this is we wanted to allow galaxies that are either nucleated or have a relatively high surface brightness core embedded in a low surface brightness structure. We wanted to allow objects like that into our sample. And by far the most important selection we're making at this point is we're focusing on galaxies that are big on the sky. And this is, again, to get around this issue of the HSC images having such a high density of compact sources in them. So this is a very powerful selection criterion. And in the end, we're still doing visual inspection. This is because at these low surface brightnesses, you really get killed by things like scattered light and other optical artifacts. And also, there's a lot of interesting astrophysical sources at these surface brightnesses that begin to pop up, like tidal fluff from galaxy interactions or galactic cirrus, which we struggled quite a bit with in a few of our fields. So after running this pipeline, we have a sample of about 800 low surface brightness galaxies that we published this year, and so the catalog is public. And this is over the first 200 square degrees of the HSC survey. So here's our sample in a color plot. The color distribution appears bimodal. So if we just divide the galaxy in half by the median G-I color into blue galaxies and red galaxies, here's an example of the sorts of objects that we're uncovering. So the blue subset tend to be these lumpy, irregular galaxies that often have clear star formation going on in them and big knots of star formation that you can see. And the red galaxies tend to have smooth morphologies. They get to much lower surface brightnesses than the blue galaxies, and they're a lot more clustered. So it's looking like they're sort of dwarf elliptical type galaxies that are associated with galaxy groups. So one of the first things I did when we got our catalog was cross-matched it with a bunch of other catalogs in the literature. And one of the most interesting results that we found from that is that a good fraction of these objects are also detected in GALEX, something like half of them, most of which are the blue galaxies, not surprisingly. So these are those objects I showed you previously, but now we're looking at them in the GALEX pixels as well. So this is really neat for a number of reasons. One, if you want to do SED fitting, this is great. But also, we see in like the SDSS image where you can barely see anything at all. There's just a booming signal in the UV. And so this suggests that GALEX could be a very powerful resource for going and finding more of these sorts of galaxies. So if we take all of our galaxies for which we have some sort of distance information, whether that's archival redshifts or arguments based off of clustering near known galaxy groups, I can plot them on a size luminosity plane to get a sense for the spread of physical properties that are spanned by our sample. And so here they are. The big triangles and stars are galaxies from our sample. And then for reference, I'm showing the family of early type galaxies. And then these orange squares are the UDGs that were discovered by Van Dockum in 2015. So the main takeaway from this plot, and really about our sample in general, is that it's really diverse, just like the low surface brightness galaxy population. It spans these are dwarf ellipticals in nearby groups, up through the UDG population, and then even including the sort of low luminosity end of these giant low surface brightness spiral galaxies that were being uncovered in the 90s, which are indicated by these black diamonds. The reason why I've highlighted these points in green is because I just wanted to note that we were awarded 20 orbits with HST to observe these UDG, should really call them candidates, that were clustered around low-density galaxy groups. And the goal of these observations are to count globular clusters in these systems, both as a distance proxy, but also as a probe of their dark matter halo. So we're hoping to get those observations. We thought we were going to get them this year, but it turns out we're going to get them next year. So hopefully that goes through. Now, so we've learned an awful lot about these galaxies just based off the limited distance information that we have. But as is the problem for all of astronomy, at some point is we really need more distances if we want to begin to understand these galaxies and place them in the cosmological context. So this is an effort that we've started. So we figured the first thing we should try is to go after the galaxies where we really thought we could succeed at getting redshifts. And so the obvious choice were these objects that have very strong GALEX detections. So we recently posted a paper on the archive where we got, as a pilot study, we got long-slit GMOS spectroscopy for 2 of these blue galaxies. We used the fact that they have very strong GALEX detections to say that we thought we would detect H-alpha, and we definitely do. So here's the spectra of these objects. You can very clearly see very strong H-alpha emission in the 2D spectra. We also detect a couple other emission lines in these galaxies and 2 marginal detections of N2 in both of them, and then O3 in one of the objects. And so with these distances, we can now begin to ask questions about their physical properties and their environments. So the two objects that we got the spectra for are shown as these red stars. Now for reference, I'm showing dwarfs in and around the local group, and shaded here is the region where UDGs live in this plane. And so what you see, these first two objects, which are one's at 25 megaparsecs, and then this one's at about 40 megaparsecs, they're at the small size end of the UDG population. But what's very interesting about these two sources is that they're very isolated in space. So we're talking 2 to 3 megaparsecs to the nearest massive neighbor, and more than a megaparsec to the nearest dwarf to these objects. And so, whatever mechanism is puffing them up is likely internal in origin, something like high-spin halo or episodic burst of star formation or something like that, to explain the sizes of these objects. I mentioned we got a few other emission lines. This allows us to say something about the gas phase metallicities. And so our objects are shown as blue and red here, and the main takeaway is that they appear to have relatively high gas phase metallicities for their stellar mass. So all the other points are reference galaxies of low stellar mass. Now this is a small sample size, and our measurements are very noisy. This wasn't originally our goal, but if this trend continues for these blue puffy galaxies, it'll be an interesting thing to note. Now we got long slit spectra, so do we see any kind of rotation? And again, this wasn't our goal. We just wanted to get redshift, so we were way too conservative on our slit width and things like that. But we do see evidence for ordered rotation in one of these galaxies. And while we don't have the resolution to do detailed mass modeling here for comparison, I'm just showing you dwarfs. So our points are the green, and then these lines are dwarfs of comparable stellar mass that have had high resolution rotation curves and detailed mass modeling done. And then the picture here is just that this object appears to be consistent with living in a dwarf-like halo mass, which perhaps isn't surprising. Its stellar mass is a few times 10 to the 7, but this is just it's a data point to add to the question of making a connection between these extended blue puffy galaxies in the field and the ultra-diffuse galaxies in clusters. And this is a picture that's consistent with many other studies that you should check out that have made some sort of rotational measurement of a UDG. So we're going to keep getting more spectroscopy, but we still want to get more distances. For the majority of these objects, they're going to be too low surface brightness to get a significant number of distances for them. But we can get distances in a statistical sense by taking advantage of the clustering of galaxies. And so the way we can do this is shown here, where the red is our footprint of our survey, and the blue are galaxies in our sample, and the black is just a reference sample of galaxies of known redshift, and the animation is stepping through bins of redshift. And then the way we play this game is we take our sample of unknown redshifts U, and we calculate the angular correlation with the reference sample of known redshifts, and we do this in bins of redshift. And then we can average over the angles in each bin, and this gives us some sort of handle on the redshift distribution of our sample. And so I've done this for the red and blue galaxies separately, and here's what we find. So it's a noisy measurement, not very many galaxies. But what we see is the vast majority lie within a redshift of 0.1. I think that makes sense. We've cut on large physical size or large angular sizes, so we expect them to be very nearby. And they span similar distance ranges. But one interesting point is it looks like the red galaxies are preferentially associated with overdensities at very low redshift and a redshift of about 0.075. And when you look at the reference sample of galaxies, that paints a consistent picture. So I'll finally note on some stuff that I'm working on right now is we want to be able to take this understanding of the redshift distribution and say something about the space density of these galaxies as a function of surface brightness, but a crucial component to that is completeness, which is what I'm working on right now, is doing image simulations to try to measure our completeness as a function of galaxy parameters and position in the sky. Very preliminary, but I've run through the calculation, and here's results where we're showing purple as the space density of these galaxies as a function of surface brightness. And then for comparison, I'm showing Julianne Del Canton from 97, which is one of the lowest surface brightness measurements of this number, and we're finding consistent results with her, as well as a value that appears to remain flat at even lower surface brightnesses. And for reference, the distribution is well known to remain flat from surface brightnesses similar to that of the Milky Way all the way out to these very low values. And so I think I'm out of time. I'll put up a very simple summary of the talk and gladly take questions. Yes. It's interesting. We haven't done that. The GALEX pixels are ginormous, but it's an interesting question. I mean, you can barely, clearly see regions where there's a blue knot associated with lumps of blue in these images, but we haven't actually done that sort of calculation. That would be interesting. I suspect we'd only be able to do it on the galaxies that are the absolute biggest on the sky, given the GALEX resolution. You can do this, color gradients. Oh, an HSC, sure, yeah. The what now? The Hubble? What? Oh, globular cluster? Am I able to do what now with them? Oh, with HSC? That's a really good question, and we have somebody working on that right now, and definitely there is a regime. It's not quite clear to us yet where that falls, but there will be a small number of them that are very nearby where we can actually see some globular clusters, yeah. Oh, yes. Oh, right.